Recording. Okay, so let's conclude what we were talking about, our last topic here, which is on the Z transform, and just some little updates. Well, first off, I'm almost finished marking the other class, the midterms, and I'm about halfway through. Good morning, Stephen. And I'm halfway through marking the midterm for this one as well. All right, so you'll get back those results after. It is very cumbersome. Normally, what I would have done is that if we had paper, I'd come to class with your scripts and just divvy it up into piles and let you all retrieve your paper. But here it is after we upload it for you to have access to, and that's a kind of one-on-one um, scramble here. So let me just sort that out for you. But you'll get your marks before even, and you will get back your papers, right? That's one. Now that's for both courses. Last night I put up a little shareable document, so you let me know if you can access it. And that is for you to put in your areas for clarification or concern and so on. And don't put in things like the whole course, eh? All right? But put the specific topics where you may need some clarification on. And I'm working out so that next week sometime we'll have some revision sessions for both this course and the other one as well. Okay, and I'm sort of curating some past paper questions for the other course that ECNG 2012 that you'll get today. So that at least example questions so you can see how sometimes the questions are asked. This is how I'm teaching it this year. This is the first time I taught it, so my questions will be not too different from the last time, but there are some things that we didn't cover, so I'm not going to ask you things on that. All right. So let me see what else. Oh, right. And we are in the process of a quality assurance review this week, the department. When you start to work and you're working, depending on where you're working, periodically. Thanks, Bridget. So yes, when you're working, depending on where you're working, you're going to be subjected occasionally to things like quality assurance visits and audits and the like. And that, of course, it's a check to make sure that, especially when you're dealing with external parties and the like, that what you're doing conforms with the requirements of other people, so that, like in your case, that your qualifications and the things that we teach you are transferable. So people have to come and check every so often, and we're in the middle of that this week. So, well, in any case, I'm planning to finish both this the signals course this morning now, and the electronics this afternoon. Just have a minor thing, so there wouldn't be any class tomorrow. And in any case, I would have been in the middle of some sessions with the auditors at that point anyway. But I've put up the document, and you feel free to populate it with whatever you want clarification and whatever is troubling you with the course material. Just make sure you put the right thing in the form for the right course, and well, we'll take it from there. All right. So today, let's finish off what we were talking about. Right, just a little review here. So, right, so a recap. Remember the continuous time system model, which is how we kind of started out this thing way back when. The world is a continuous time world. The signals that we measure, and specifically as electrical engineers, we measure voltages, currents, or resistances, and every other real world parameter, temperature and pressure and velocity and acceleration, all end up being converted by a sensor or sensors and electronics into some voltage or current or resistance. So our input in our continuous time systems are these signals here. And we have the system. Continuous time systems are the kind of things that would be implemented using, for example, what I have on the screen here, operational amplifiers, passive networks, resistors, capacitors, inductors, and the like, induction motors, all those kind of things. So it takes the input and we get some output in response. The output could be anything from another set of values to a voltage that is going to control the speed of the same motor, or in a car, the output might be the direction that the car goes in response to your turning the steering wheel, all of those kind of things. We went through those millions and well, millions of examples in theory possible. And we saw, most importantly, that in the continuous time world, that the relationship between the input and output was a convolution. So the output was a convolution of the input signal and the output signal, sorry, the input signal and the system response. And we use the Laplace transform to perform the convolution for us in most cases, so that for us, the thing that we grew accustomed to is that yx will be the Laplace transform of xs multiplied by the Laplace transform of hs. This, of course, we call the transfer function, right? But just to illustrate, there were some things, for instance, a simple thing like a rectangular pulse. Trying to get the Laplace transform of that is harder than trying to convolve that with another rectangular pulse. It can be done, and there are some past paper questions that ask you simply to show that if you were to use the Laplace transform to convolve two pulses, for instance, that you get the same answer as if you were to use the mechanical or the manual approach that we did in lectures, I think 10 and 11 kind of thing. All right? The discrete time world, you take this, the continuous time world, and then you put in some other facilities in it. The first sort of block is that from the continuous time world, we have to convert that into some numbers. Discrete time signal, discrete time systems take numbers in and give you numbers out. So to go from the continuous time to the discrete time, we have to do this thing called sampling. We mentioned a little bit about that and the sampling, and inside of here, of course, is the sampling process itself, right? And then the conversion that Dr. Radix did the lecture on. So once you go through here, the continuous time domain, you remember, it's the signals doing that. The discrete time domain are a series of numbers that represent this. And remember, sampling is like you multiply this by an impulse train. So what you're going to get here will be a value here, a value here, a value here, you know, those kind of things. And these values with the analog to digital converter actually convert it to numbers. So it's going to read a value. So you're going to have, you know, 1.47 minus 2.34.001, and so on. Those would be the xn, the equivalent values of xt, whatever xt happen to be. And the discrete time system works on that. What is a discrete time system? We saw there were examples. Of course, the one that you all and we using almost without thinking about it is a microprocessor, right? We're on a computer here, and the computer is churning away numbers. When I speak, my voice is being converted into numbers, and the microprocessor of the system is manipulating those numbers in a way that it can be transmitted, sorry, to you. And at the destination side, the numbers reach, and they are reconstructed. And how they are reconstructed, so a little bit about that you have the numbers coming back now, and the digital to analog conversion, which was also spoken about, DAC, sorry, digital to analog conversion. Well, look at this. So it will hold this value, then hold this value, then hold that value, then hold that. So you get this kind of signal coming in, right? Which is an approximation of what the original signal was, the continuous time signal was. And if these steps are small enough, you get a kind of a fairly good real world a reconstructed world approximation of what the continuous time signal looked like. Every time you take a picture with your cell phone, this is in fact what is done. The continuous time signal comes in through the lens. The sampling and the converting to numbers is done by a sensor behind the lens, something called, you would have probably met it somewhere else before, a charge coupled device. And each dot on the charge coupled device will produce a pixel or a bit of data coming out. The phone system now will take all of that information that was sensed there, and it will do all of this here to convert it into something called a JPEG. And the output is, of course, a JPEG file that is saved somewhere. Right? So again, we're using these things almost all the time without even thinking about it. And I keep stressing, the output-input relationship is again a convolution. And what we said last time now, in the discrete time domain, we use a different transform now, which was the Z transform that we introduced last week. So that in the Z transform equivalent of that convolution will be YZ equal XZ by HZ, right? Where the Z is a Z transformed version of the discrete values. Yeah, so everybody kind of in the cobwebs of your mind, they're recalling that, I'm hoping, right? So that kind of revise the whole course in 2 slides there. And then we saw that specifically for discrete time systems, which is what we're dealing with now, the discrete time systems are represented by something called difference equation. And the difference equation is an equation that represents the current output in terms of current inputs, past outputs, and past inputs as well. If the system is causal, then you don't have to worry about the past inputs, but the system itself may have memory that relates to the past output. And we know this again from simple digital electronics, things like shift registers, for instance, where it moves depends on where the current state is and where it was before. Counters do the same thing. And last week we saw that it is easy now to, almost by inspection, that you can go from the difference equation to the Z transformed equation, because every y kt will transform to a yz. If we delay by 1, and we went through that property, this is a first order difference, right? Our first order difference here. This would give me, because it's a delay, a z minus 1 yz plus the initial, plus an initial value on y, right? And then of course you have to multiply it by the coefficient here. The same thing for the x's as well. And if the initial conditions are 0 and the input is causal, so for instance, if it was again like a shift register or something like that, and when you turn it on, you reset everything. You remember these things like shift registers and counters and FPGAs and so on have something called a power on reset that you have met somewhere. So you reset the whole thing. So there's no memory of what went on before, and any input is causal. Then you could neglect all of these conditions, and the equation very easily transformed into this form. And then you group the y's on one, the yz's on one side and the xz's on the other, and you have your transfer function. Yeah? And you could do it by its inspection. As we said, once you know it, if you have no initial conditions and no and causal inputs, then you could you translate it straight off. And if, for instance, we had an A1 y k t minus 2t, right? I have to keep remember to put square brackets here just to distinguish it from the continuous time domain. Something like this would give me an A1 z minus 2 y z. Yeah. Remember, the z transform is just a summation, right? It's a simple summation x n, right? Z to the minus n. And n can go from minus infinity to infinity for the two-sided transform, or from 0 to infinity for the one-sided transform. Yeah? Everybody remembering some of that? That's somewhere along the place we covered that, right? Joke, we did it last week. Right. So once you have that, then you could solve a problem like this. Now, this is the kind of questions that I could ask you, and I ask you all the time, and it appears. So this one, you have a system here, and you have some, or you have a first order you have a difference equation. This is a second order difference equation here, because we have a y minus 2t here, right? And we have some initial conditions. So to solve this, you apply the Z transform to it, and the Z transform, of course, will give me y z right here, and this will be 0.1. And now inside of the bracket, now we have a first order difference, so it will be z minus 1 y z plus y minus t, right? And this bit now, this is a second order one, so this is going to be like 0.02 into, since it's a second order, it's going to be z minus 2yz. And we're going to have, because it's a second order, it means that we have two of these values going to come in. So this one is going to be shifted from by 1. Remember the graphic we did last time? So it will be z minus 1 y minus t plus y minus 2t. All right, make sure and put everybody in the brackets, and then you do the same thing for xkt and xkt minus t. Then once you do that, you open up the brackets and you substitute. So y minus t is minus 10. So you're going to substitute for that here and here. Y minus 2t is 20. So you're going to substitute for that here. Xnt is a discrete time unit step, which means that x minus t is what? If it's a discrete time unit step, x minus t is what? See, this is where if I had the people in front of me here, I would have picked somebody to answer the question. You know. X minus t is what? I could go to the list and call, you know. X and t is a unit step, right? So x, if I were to ask you x minus 1 for argument's sake, or minus t, which is minus 1t, right? If it is a discrete time unit step, x minus 1 is what? 0, yeah. Right, you know, it's a unit step, so everything before 0, everything less than 0 is 0, right? Causal, exactly. All right, so just so once you're given that, so this here is a shorthand way of saying that any value x minus t, x minus 2t, etc. are in fact 0, all of them. So if you make these substitutions, if you expand this, make the substitutions and do it and do the algebra and arithmetic carefully, you will get an answer looking like this. Okay, so that's your little double check that you have to do here. And we can now start to express this in a slightly different form. This equation, I can start to factorize. Now, this is the system here in response to our unit step, right? So there's not a transfer function here. We've substituted for xz inside of here. Once I do that now, I can start to factorize both the numerator and denominator like we would have done in the continuous time domain. So I could find the factors of this, and I can find the factors of that. Usually, if I'm asking you to do something like a third order, I will give you at least one of the answers, right? Another thing to look at, and we'll come to this in a second, is that if you are asked to factorize this, okay, some of you all may be a little bit uncomfortable dealing with negative indices. There are some people who it throws them off a little bit. So you have a couple of ways of doing this. You can multiply this. I have some people, yeah, okay, not a problem. You have two ways of doing this. As I said, we prefer to work with a negative index domain because z minus 1 translates into a delay in real time by minus t. So every time you see that, so if I have something like z minus k, I know that whatever was associated with this was delayed by minus k. All right, but for the purposes of manipulation, and for people who again have little issues dealing with the negative indices and so on, if you want to move from this form into the form like to get the poles and the zeros, for instance, all right, you need to factorize the expression. What you can do first off is that you could look at this thing, and if I multiply this by z cubed over z cubed, I can convert this entire thing into positive powers of z. And then once that is there, I could proceed to factorize as normal, right? So if I were to do that, I could convert that entire thing into positive powers of z and factorize, right? I kind of did both things together in one step here, right? So that's one approach. The other approach that people sometimes take is to let some dummy variable, right? And you have to pick something of a, what shall I say, a constant that is not associated with anything else. So you let some dummy variable like a, for instance, be equal to z minus 1. So I could express this now as 1.4 minus 0.6a plus 0.2a squared. And below here would be 1.1a, 0.08a squared, and so on. And then I could factorize it here and then we make the substitution at the point, right? Until you get comfortable working with these, right? We would prefer not to see this because next thing you leave the answer in that form, or you go on to get an answer that is in another variable. Don't use x, y, or God forbid z, because we in the z transform. So you wouldn't want to say let z equal z minus 1, of course. X and y are usually the inputs and output values. Don't use s, because s is the variable associated with the Laplace transform. So you can pick some other number. I suggested a, but you can pick any other thing that you want, and you can work with that, right? So you have two choices initially. One, you can rationalize the whole thing and work with it in positive indices, or you can make a substitution, and the substitution will allow you to factorize it, but then you have to convert it back to the resubstitute to get it back into the negative index form. Both work, right? This one is good to guide you along the way to get you accustomed to working in the negative index domain, right? And it's kind of like, well, it's basically kind of like when you were learning to count before you got good at mental arithmetic, you would use your fingers, and then as you got the mental arithmetic, you stop using your fingers and did the work directly, which is what we are aiming for. But as you get familiar, you're allowed to use your fingers, but remember to make the substitution coming back, right? Following so far? So if you know, so all of these examples now, once you get it into the positive domain, of course, you can go and you can factorize, and we have the zeros and the poles, the same thing like in the Z transform, sorry, in the Laplace transform that we had. And of course, you plot this in the Z plane so you can see where the zero, where the poles are, where the zeros are, and so on. Right? And we spoke about for stability. You're not going to be asked this, but for stability in the discrete time domain, that the poles have to be within something called a unit circle. Right? So all of these things. So for instance, this is Z equal to 1, so that pole is right on the unit circle. This one is mod Z equal to minus equal to 0.2, so that's inside here. This one is something equal to minus, the modulus of that is equal to minus 1. So that is outside, inside of here somewhere. So you could see where the poles are inside or outside the unit circle and so on. You're going to use that a lot when you do controls and advanced controls, if you are going along to do those things. So again, like we had in the other transforms, we have a number, we have different ways now of representing things. The discrete time system can be represented by a difference equation. It can be represented when you Z transform it in terms of negative powers of Z, which is preferred, or you can express it in positive powers of Z, and this is what they call the pole zero form. All right. And again, I could convert this if I were to multiply this through by Z minus 1 over Z minus 1, for instance. I could convert this. In other words, this here is really 1 minus Z minus 1 into 1 minus 0.2 Z minus 1. And this is 1 plus 0.1 Z minus 1, right? Yes, Akim. What I was saying is that you remember when we looked at the Z transform last week, the properties of the Z transform is that every time you delay, you get a Z minus 1 being produced. So like for instance here, this gives me Z minus 1 YZ. So every time in an expression you see something with a Z minus 1, it means that, you remember this is in the Z domain, but in the discrete time world, which is where this is supposed to model, it means that whatever was associated with this Z minus 1 was delayed by 1 t. Okay, you remember the discrete time world is sampled every t, whatever time units those are. So Z minus 1 means that whatever was associated with that Z minus 1 had a delay of t with it. Whatever is associated with the Z minus 2 had a delay of 2t with it. Right? So it's telling you this sort of sequence of events. Remember, it's numbers coming in. So the Z minus 1, the one without the Z is the first number. The one with the Z minus 1 is the next one in line. And the one with the Z minus 2 is the third one in line. But you see that directly by the negative number here. All right? When you convert it to the positive index form, like this, looking at this here, I can't tell which is the first, second, or third number at that point, right? But I can't get the poles. So you see, everyone has its own use, right? Right? So you see, we can look at it in all convey the same information. All convey the same information. It's just looking at it from a slightly different perspective. So, of course, the thing with all these transforms, we looked at this, the Laplace in here and elsewhere. We looked at the Fourier here and the Z transform. The thing about the transforms is that they take you from one domain to another, but you always have to find your way back home, right? Otherwise, what is the point? Right? It's not a one-way trip. So having done whatever manipulation you get, what does this sequence, in other words, we got this because we started off with a difference equation. A difference equation gave us that. But what is the solution to the difference equation means finding, after you've manipulated it here, what is the inverse Z transform? So that coming back out of this, this is supposed to give me a set of numbers. And there are three ways we can do that with the Z transform. One is doing long division, which doesn't exist for any of the other transforms. Two, by doing complex integration, which exists for the other transforms, but we don't tend to use it too much. And the other one, partial fractions and tables, which is what we have been doing for both the Laplace and the Fourier transform. So the first one that none of the other transforms that you look at actually do is long division. The long division technique gives us something called the open-ended, the open form or the infinite response. I don't worry too much about what that means, and I'll tell you in a second. But what it does is it's similar to what, if I have a system and I want to find out, so this, back to our example here. So I have this here. This was this system in response to a unit step. So I have the system, right? This is this is HKT here now. HKT. I put in X, which was a unit step, KT or NT, and I got this. Now the unit step is, as we discovered, a unit step is naught, 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 and then at t equal to 0, you have you have 1, 1, 1, 1. Right? Forget this one here. So you have naught, 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 then 1, 1, 1, 1, 1. So what is the output of this? The output of this in response to that might give me nothing, nothing, nothing. It might give me, at this point, 0.5. It might give me 1.5. It might give me something here, something here, something here. And then eventually, it kind of settles down like what we know the step response for continuous time systems look like. But if I want just to find out what the first few values here are, then one of the ways that the Z transform allows us to do it that is not possible with the Laplace, for instance, is by something called long division. What I do, I simply divide the numerator by the denominator. Now you would have done things like that in your high school algebra and maybe your add maths. So this now I'm dividing this. I'm dividing this by this. So you do your normal, if you like, your normal algebra form 1.4 minus 0.6 z minus 1 plus 0.2 z minus 2. The screen is a little bit cramped, right? And then you put this out here now, the same 1 minus 1, 0.1 z minus 1 plus 0.08 z minus 2 plus 0.02 z minus 3. Well, that's very Very scrappy there. You must have them in this way. So you must start with the constants, and then you have the decreasing power of z minus 1. So however it was, you put both the numerator and the denominator in this form. And then you do your normal division. So you're looking at this one. So to get 1.4, I have to multiply this entire thing by 1.4 here. So if I multiply by 1.4, 1.4 times that is going to give me 1.4, right, minus 1.4 by 1.1 z minus 1, plus 0.08 by 1.4 z minus 2, and so on. And then you subtract, just like your long division. And you're going to get something with some, let's see, k, z minus 1, and z minus 2, etc. So the next step here will be you multiply it by whatever that is. So k by 1, and you're going to get another function with z minus 1, z minus 2, and you subtract. Yeah? Remember doing those things for algebra? Or at maths? Right? Very straightforward. Right? And the hardest thing in these things is to write it down neatly. Use paper. Use it, spread it out. Well, yeah, in a way, you just have to, it's algebra, so you just have to make sure that you copy down the indices correctly. And once you do that, if I do this, I'm going to get now the answer may or may not end. That's the difference. When I give you 72 and tell you to divide 72 by 12, you get 6 and the answer ends. That is it. When you do this long division, the answer may or may not come to an end. Right? If it doesn't come to an end, this is why we call it an infinite response. So the division could be going up and up and up. Normally, all you do is to go, you just try for the first 2 or 3 values. And why that is useful now is that if I divide this, the first 3 values of this are going to look like this, and this is going to continue. So I'm going to have something with z minus 3 here, z minus 4. This is going to go on forever, right? For a long time. And that's not the purpose of this. The long division is just to get an idea what the first few values are looking like. So if I tell you y z is this, you remember what the z transform did? You remember last week we had some values, I think was 1, 9, and minus 8. All right? If this was times 0, this translated into 1 plus 9z minus 1 minus 8z minus 2. Yeah? So if I give you this, I could get back, you could go this way now. I could look at this and say, okay, 1, so the first value is 1. Z minus 1 means that the second value is 9. Z minus 2 means the third value is minus 8. So I could go from this and immediately say that ynt, the first 3 values of that are 1.4, 0.94, and 1.12. Right? So the first 3 values of ynt in response to a unit step, remember we got this because the example was a unit step. So a unit step, the 3 values for the first 3 values for the unit step are 1, 1, 1. So this system, 1 goes in, 1.4 comes out. 1 goes in, 0.94 comes out. Next one goes in, 1.12 comes out. So immediately you can see if this system is doing, if this was a design, let's say the first value, 1 went in, and instead of 1.4, you have 107. Clearly, well, let's say it's a 5-volt system, and it's telling you that 107 is supposed to be coming out, right? Immediately you go back to the drawing board and say, okay, wait, something went wrong with my calculations immediately. It's that kind of thing. Yeah. So immediately you can see it's almost like what we would do with the Laplace transform when you do the initial value theorem, where you can see what the initial response for the system is going to be. Here you're actually getting the first few values. Making sense? Yeah? Yeah? Right. So that is one way of getting the inverse. And as I said, this is an open form response. So the answer doesn't give me for instance, this is not going, if somewhere along the road, I wanted to know what y25t was. There's a 5 here. This is not going to help me find y25t. For that now, I need a closed loop the closed loop answer of yn't in terms of things that I can substitute for t. So the second way now, so this is the first way of finding the inverse transform. You divide the numerator by the denominator. It must be in this form, right? Increasing or decreasing powers of z, or increasing powers of minus of z to the minus n, whatever, however you want to put it. In other words, start with the number and keep increasing the negative numbers going off to the right. And then you divide the numerator and the denominator very carefully. And usually you stop after the first, let's say, 3 divisions, because all you're interested in is the first few values here. The second way, of course, is to right, and this just summarizes what I said. So you know that the first value is 1.4, the second is 0.94, and so on. Right? Yes. So, and this is now, if luckily enough, after the division, after maybe 3 or 4 terms, the division ends, then we have something called a finite response, and you can actually put those numbers into a computer that is the system response. So is the kind of thing that computers and microprocessors can work with. The second way we can find the inverse response is by doing integration. And I'm just putting it here, and we're going to pay absolutely no attention to it. This is, in fact, how the Laplace transform is done for very complicated signals where you can't really break it up into smaller subdivisions and use tables and the like. And of course, the way we like to work with it is a partial fraction technique, just like we do with the Z transform, just like we do with the Fourier. So you get that, you put the Z transformed expression into partial fractions, and then you look at the table, or you go from memory if it's simple enough. And this now is going to give me a closed form representation, and this is the one where I could substitute t equal any value and find out what it is. So this is going to give me that y nt is equal to 0.5 to the power 0.3 nt plus something. So if I wanted to find out what y25 was, I just put 25 inside of here, right? Let n equal to 25. The t is understood, right? So this, as I keep saying, this is equivalent of saying yn is equal to 0.5 to the power 0.3 n. So if I want to find out what happens at t equal to 100, I just put t equal to, well, n equal to 100, sorry, and I could figure out what that value was. That's a closed form representation here. And to do that, of course, we do the usual rules for partial fractions. The first thing, of course, is that the expression must be proper. In other words, the order of the numerator must be less than the order of the denominator. If it isn't, then you do a long division once. So for instance, if I had 1 minus z minus 1 minus z minus 2, and the denominator was 1 minus 2z minus 1, right? I will divide the numerator by denominator at least once, so I'll get a constant plus at least one something plus z minus 1 over something plus z minus 1, right? So less than or equal could work as well. So less than or equal will work, but it must never be, the order of the numerator must never be greater than the order of the denominator. Then once you do that, then to do it in partial fractions, of course, as I mentioned earlier on, you're treating z minus 1 as the variable. So an expression like this would translate into, in our normal things, they are simple. The normal rules of partial fractions apply. So this is going to be some a over z 1 minus z minus 1, some b over 1 minus 0.2 z minus 1, and c over the 1 plus 0.1 z minus 1. And you solve for a, b, and c as you're accustomed doing. This is where I said, if you don't like to work with a z minus 1, you can let some variable, well, we're already using a, b, and c here, so you let some variable that you will resubstitute afterwards be equal to z minus 1. Okay? What's a good variable to use here? That seeing that we have a, b, and c, little d, e, f, g, h, I, j, k, m. I don't know, you probably want to let m equal to z minus 1. Pick something. Not s, not x, not y, not z. All right? You can probably, and not w, w like omega, so don't pick that either. So pick every other letter in the alphabet. Don't pick I and J as complex numbers. So you're kind of restricted, right? A, B, C, so you can probably use D if you want. So this would have been A over 1 minus D plus B over 1 plus 0.2 D plus C over 1 plus 0.1 D. And you solve for A, B, and C as you would have done for the your normal situation, right? The normal partial fraction situation. All right, so you could solve. So in this particular case, I don't know if you know, when you're doing partial fractions, you could either get 3 simultaneous equations and solve for A, B, and C, or you can use, I think what they call it, the sort of cover-up technique here, right? So for instance, if I wanted to solve for A, remember this is equal to this. So if I want to solve for A, if I multiply both equations, if I multiply here by 1 minus z minus 1 and multiply this side by 1 minus z minus 1, right? And I set z minus 1 equal to 1, right? Then on the left-hand side, this will cancel this, and then I can substitute z minus 1 equal to minus 1 inside of here. Z minus 1 equal to 1 will mean that these two equations come out. I cross multiply by this, so I'm letting A now equal to that expression here. So in other words, I'm solving directly for A. So by doing that, I can solve directly for A, I can solve directly for B, and I can solve directly for C. Or if you prefer, you can write out the 3 simultaneous equations. So you go back, you cross multiply, right? You cross multiply and you'll get 3 equations for A, B, and C. And you equate coefficients and you solve the thing simultaneously, right? If you were using a substitution, so like I said, if somehow inside of here, that you had this as d equals z minus 1, right? Then you have to now resubstitute in the end to get it back. Fair enough? So once you do that and you solve for a, b, and c, you get it into this form. And you go to your z transform tables. So something over z minus 1, right? 1 over 1 minus z minus 1 is unit step. Exponent is something over 1 minus a z minus 1. So these two are two exponents inside of here. And of course, if you had more complicated ones, you just look up in the z transform table like you did for the Laplace transform, like you did for the Fourier transform. And the same rules apply for partial fractions, all right? Repeated roots. So repeated roots, for instance, if I had, somehow I had 1 minus z minus 1, and I had 1 minus z minus 1 squared, for instance, right? You have the same rules for repeated roots. You have the same rules for quadratic roots. So on top here, whatever, an az plus b, that kind of thing. Yeah? Everything that you have done many occasions before applies. The only little unusual thing for the z transform is this, that you're dealing with z to the minus 1, whereas the Laplace transform was a straight positive index s squared s cubed s to the power 1, or in the case of the Fourier transform, you had j omega raised to a particular power. All right? But there's a way around that. As I said, you can make the substitution. Nothing wrong with that, but make sure and substitute before you go back to the tables. The tables are expressed in this form. Right, so you have to get your answer, whatever substitutions you made for z minus 1, you must get it back in this form before you can look it up in the tables. And if you did that correctly, then the final answer, the closed form answer for that question is supposed to be this. Right? So here, one way to check the closed form answer is, for instance, if n equal to naught. If I put that in here, I'm going to get 1.136, right? N equal to naught in here. This is the power naught is 1 minus 0.567, right? Plus 0.83. And if you work out that, this is supposed to give me, what was the first value that we worked out here? That's supposed to give me 1.4. Yeah? And then if you substitute n equal to 1, if I substitute n equal to 1 here, then I'm going to get 1.136 minus, well, 0.2 to the power 1, so it will be 0.567 by 0.2, right? Plus 0.83 by minus 0.1. And if you plug that in, you're supposed to get, what was the second value? 0.94. Right? And n equal to 2 is supposed to give me 1.12. Fair enough? This is the closed form. So I now could find, for instance, if I wanted to find y, oops, wrong color. Y65 for argument's sake. I could put n equal to 65 here, here, and here, and see what the answer turns out to be. This is why it's called a closed form solution. So you could get any of the values. Now you could generate any of the values that this system would produce. So for instance, if I were to see what the first 100 values of this is, I could just now do a simple iteration. There's something that I could put into a little loop, n equal to 0 to 100, and generate the first 100 values of y and t and see what it looks like, and then plot it. Yeah? Make sense? right? This you have to listen again. Well, we have all the past paper questions, of course, to go through and practice this. Do the examples here. Again, follow through what I said. We will have review sessions coming up. Has the exam timetable been put up as yet, by any chance? This is 9 o'clock, so let me think. Right, so when is our exam? ECNG 2011 as well. All right, okay, so we have a few weeks ahead of us, right? For ECNG 2011, this one is it afternoon of the 20th. Who does a Christmas gift? Okay, so we have time for review next week. I'm going to have review sessions for this and for the other class as well, right? So we have time to clarify things. You have past paper questions. We're still deciding that, Jared. I think the exams will be communicating. I think what do you call it? Bridget would have circulated something from the head of department over the weekend, I believe, so that we're going to the face-to-face, any decision on face-to-face exams will be contacting students and communicating with you all directly about it. Okay, the students not in Trinidad, I think the arrangement, if I'm not mistaken, is that the exam will be administered through your through the open campus in whatever country you are in, right? But all communications concerning the exam is going to come from the exams, not from us or not from me. Okay, so if we find out anything other than that, the head of department will let me know and I'll pass it on to you. Okay, so I'll run over time here. Let me not keep you back too much. So this is the end of ECNG 2011 for this semester. So an early Merry Christmas, right? Of course, we'll be meeting sometime before. You have work to do. You have revision to do, of course, and you have other courses as well. Write down your concerns in that Google Doc that I put up as well. And of course, I'm hoping that you continuing. The good thing is that you can at least listen to some of the lectures again and clarify matters. So I'm hoping that turns out to be helpful for us. All right. So let me hustle on to your other class. I have this quality assurance visit. Yes, it is the most wonderful time of the year until you get the exam. So let me go on to my quality assurance audit. And guys, I'll see you all this afternoon at 3 o'clock. Will we be tested on all topics in the exam? Well, just look at the past papers. You'll see I generally have a question on everything that we do in some form or fashion. Yeah. All right. So let me stop the thing.